This is my homebrew 8-bit relay computer project, and I've been working on this for just under 2 years now. It's still full on in construction mode, but it's already able to execute a program. Now that program was really short and sweet. Just 2 bytes or 2 instructions that loaded the A register with a value of 12 and then halted the clock. And although that was a very simple program, this machine is capable of much more complex things. For example, I could add these cards like the ALU adder, the ALU logic unit, and then the supporting B and C registers to do math functions with this machine. But because these current backplanes only have 5 slots available on each, I would need to add a third backplane, which in itself isn't a big deal, except for the fact that when it's all put together, it simply won't fit in the case that I want to use for this project. So in this episode, it's time to design and build a bigger, better backplane. No offense. The current backplanes have been doing a fine job and have provided a good testing ground for accurate card spacing and power distribution. But as mentioned in the intro, 3 of these backplanes simply won't fit in the new case that I want to use. And with the front panel support braces in place, I'm left with a width of 36 centimeters, which should still provide plenty of card space. And while I've got the hood open, so to speak, I'm going to make some changes to the design. And right off the top, I'm going to increase the overall thickness of the board, just so it can better support all of the cards at once. And speaking of cards, since more cards equals more amps, I'm also going to increase the copper pore weight and the width of the traces. And then finally, I'm going to add some fuses to the board, just in case there are any shorts or overload issues. The schematic part of this exercise was pretty straightforward since it was just a cut and paste exercise for all of the edge card connectors. And aside from the number of connectors, the only other big difference is this new fuse that you see here, with each fuse supporting 4 cards. Once I had the correct board dimensions dialed in, it was time to place the connectors on the board. The spacing that I'm using between the connectors is identical to the existing backplane because that one has been working out perfectly. And once they're all in place, it's time to make use of the vertical alignment tool to get everything lined up. Thankfully, I figured out after a while that I don't have to draw each trace individually, but instead I was able to cut and paste small sections of the traces, which at least saved a bit of time along the way. But even with the cutting and pasting, I still want to fine-tune all of the distances between these traces. Although this was by far one of the simpler boards from a schematic and routing perspective, it was quite the task and almost a marathon event to get from one end of the board to the other. And once it's all done, I switched to this coppery view to provide some better contrast for quality control. And once that's done, it's time to admire the 3D view create the Gerber package, and then it's off to PCBWaaaay. We all know that PCBWaaaay has state-of-the-art cleanroom manufacturing technology to deliver the highest quality products. But they are also a huge supporter of electronics hobbyists through their amazing community portal and their YouTube channel that has frequent uploads of insightful how-to videos. It's so exciting each time I get a package from PCBWaaaay, and I'm thankful that they always arrive safe and sound thanks to their highly effective packing techniques. And all of this means that your boards will be fresh, clean, and ready to go. And that's what it's all about. So check out PCBWaaaay for your PC boards, 3D printing, and even injection molding needs. They truly make your projects come to life. Before I start assembly, I always give the boards a quick continuity check. And while I've never found a problem before, I think that it also helps just familiarize myself with the board. I have exactly 16 of these 128-pin edge card connectors, so I'm going to have to make every one of them count by being careful during the assembly process. Now I need to solder the underside, but my trick to use tape or elastic bands to hold things down just won't work here. So I'm going to use another copy of the same PCB and carefully give this entire thing a flip. And seeing this side now has me realizing that this is going to be a lot of soldering. Before I get too carried away, I'm just soldering a few of the joints on each card, just to make sure that nothing is wonky with the alignment before I solder everything down for good. You may have noticed that the solder smoke gets drawn away, and that's because I'm trying out this new fan that pulls those fumes through a filter. And I'm not sure if it actually removes anything harmful, but at least it keeps the smoke out of my eyes. To install the smaller components, I first tape them down, and then just solder a couple of pins using my fingers to keep it firmly against the board, and I find that this keeps everything just right when doing the rest of the pins. Next is the installation of the fuse holders, which takes a lot more solder than I'm used to. Once the power connectors are installed, it's on to placing the standoffs, and then the final act, installing the 4 2-amp fuses. Now that the backplane is done, it's time to depopulate the old ones. Before removing the program counter, I'll just need to remove these lines that are wired to the memory address on the front panel. And then I move on to removal of the last card. And with those removed, I can disconnect the power supplies running to each of the backplanes. And then it's on to this chaos of wires, which are only here because the prototype for the front panel needs to be connected to many of the control and data lines. Now the ribbon cable makes that easy enough between the two backplanes themselves, but for these other ones, that'll take a bit of time and testing to ensure that it's done right on the new backplane. I've had to create some extended control lines, and I'm sure that everything is hooked up correctly, but there's only one way to find out, and that's to first install just enough cards to test out some of the front panel operations, and then power it up. After a couple of minutes of not needing a fire extinguisher, we can try some operations. And since that went well, I'm going to spread the cards across the 4 segments of the backplane. I know this won't test all of the possible control signal combinations, but at least it will find if there's anything obviously wrong with the lines or the power distribution. So far, so good, and I think we're ready to test the entire rig. I'll start by putting the first 4 cards back to one side of the backplane again, and then, for the first time ever, I can install all of the remaining cards that I've built. This card is the new J register that is used to store the memory addresses when performing a go-to or jump operation. And then for the remaining registers, I'm just providing a bit of space so that we can more easily view the register values. Finally, I just need to connect the ALU cards to each other and directly to the B and C registers. The Fibonacci sequence is one of those gold standard tests for homebrew computers, since it requires the computer to perform both math and branching using a stored program. The sequence is built based on adding the preceding 2 numbers together to get the next value in the sequence. So if we start with a sequence of 0 and 1, and we add these together to get a 1, this becomes the next number in the sequence. And then we take the last 2 numbers, perform a sum, and that result becomes the next number. And then from there, it's just rinse and repeat. Back to the relay computer. We'll use the ALU and the B and C registers, as well as a register to hold the result. We'll start by initializing the registers with these values, and then we perform a move of the value between the B and C registers, and then the A and B registers. Next, we perform the ALU add function, which stores the new result back in the A register, giving us the first value in our sequence. Then we just need to jump back to the start of this process again, shifting B to C and A to B, adding them, and then placing the result in A, which gives us the next value in the sequence. And finally, we'll want this looping to continue until the value is too high to store in the 8-bit A register. So from a code perspective, it's pretty simple and looks something like this, which I know should work since Paul Law ran a similar program on his relay computer simulator. it ran Fibonacci perfectly. And it wasn't just a fluke. I ran it 5 times, so it's definitely working as it should be. The backplane and all of the cards are performing beautifully. So I consider this a success. And now I have to work on this part here, this prototype madness that's going on for the front panel. That's something that I still have to tweak a bit. I think that the final piece of that puzzle is just getting the output from the A register onto the front panel somehow in a binary format, but maybe also another more user-friendly sort of format as well. And that's my teaser for an upcoming episode. For now, this one's a wrap. I'm so happy. I'm going to keep playing around with this machine, record some footage for the end part of this video. And with that, thank you so much for watching and all of your support on the channel. And I'll see you next time.